survived another SolidWorks World. Last session of the conference. This is the first time I've presented at the very, very end. I've been the first one a couple times. They announced San Diego again. I guess that's a good thing. It's a good venue for next year. If you're still here and this is the last session and your brain is even half engaged, you all want to hear about geometric dimensioning and tolerancing. So there's something terribly, terribly wrong with you all, which is good to hear. I'm in good company. You'll find this presentation up on my website. I don't know if anybody has a little clicker to take the picture. In a couple weeks / 2 months, SolidWorks will have this up there with the audio. I thought they were going to do some video too, but I guess they're not doing it on very many of the sessions. But you'll definitely get the audio and definitely get this. And I'm going to reference back to 2 other old SolidWorks presentations too. So go up and look at them. Who I am, this is my 6th time at SolidWorks World. I went the first time with a free pass, didn't really want to go, and I've been going every year since. My 3rd time to present here. I am the co-chair of the North Texas SolidWorks Users Group. If you don't participate in user groups in your local area, shame on you. You really, really should. It costs nothing to join. Just get on an email address and show up once every 3 or 4 months for a meeting. I got my bachelor's of science in mechanical engineering at Oklahoma State. Got my master's degree at UT Arlington. I went for 2 different PhDs and failed both times. Just hard to write that big dissertation, so I'm a 2-time loser. I'm what they call ABD, all but dissertation twice, so that's really good. I don't consider myself an expert. Yeah, I passed the exams, the ASB exams and stuff, but I consider myself more an aficionado. I know the rules. I use them most of the time. I can advise other people really well on what they shouldn't do. So there's my Twitter account. I don't tweet very often, but anybody familiar with Hitchhiker's Guide? Do I have any really major fans of Hitchhiker's Guide? Oh, I do have some. Okay. I'll have jokes through here because GD&T is just the most boring thing in the whole world, so I tried to throw some humor in here. His trilogy was made up of 5 books. In fact, they're writing a 6th one now, posthumously from some of his notes. They're writing a 6th one, and I've been told they're still going to call it the Enhanced Trilogy when it gets to 6 books. Well, this is my 3rd time. In 2009, I presented a topic. You go back and look at the archives. It's called How to Spell GD&T. And we went through the 14 major symbols of geometric dimensioning and tolerancing. I'm going to touch on that for just 5 seconds today. I'm going to kind of go over that. But you go back and view that one. In 2010, I presented one, which was a kind of a follow-up to it, was How to Spell GD&T Part 2, The Revenge of the Circled Letters. We went through all the modifiers. That's up there on the web, on the forum. It actually has the audio along with it too. So you get my nauseating voice for 45 minutes. It concentrated on the modifiers. There wasn't an obvious 3rd one to go after, so I went a little different tack this time. We're actually going to talk about tolerance zones and shapes. Going to be the big push today is what are we controlling when we put GD&T on drawings and stuff. So leaving the theme of Star Wars, now we're in the Hitchhiker's Guide galaxy. As soon as you read the book, it says the reason why people buy the Hitchhiker's Guide is because it was a little cheaper than the Encyclopedia Galactica, and that it had a big button on the front of it that says, "Don't panic." But from my remembrance of the book, when you pushed it, nothing happened when you pushed the button. So that's kind of what we're doing here. When you do GD&T, please don't panic, and regardless of what button you push, it's probably not going to help or hurt you. So 42 in the books, that's the answer to life, universe, and everything. When you look at GD&T, there are 14 symbols of GD&T. They're broke up into 5 families: form, orientation, profile, runout, location. And we kind of grouped them that way, and that's that first class I was telling you about that happened many years ago, the Foprol chart. There are 14 symbols. They each have a name, a symbol, and a control they produce. 14 times 3 is 42. A coincidence that that's the answer to everything? I think not. Seriously, it's a better way of organizing the GD&T that I came up with of how to train people that didn't want to learn about GD&T. It makes you kind of feel good. In 2009, they updated the standard for the GD&T standard, and when they did, they started revising how they group the GD&T symbols, and they're not quite to FOPROL, but they're really, really close. They're starting to split up a little differently because it was extremely hard to read the standard and to understand what they control and how it controls things. Which brings us to the full-up FOPROL chart, which is, this is what it looked like in 1994. We're using the standard, the green standard a lot of people have on their desk. Your drawings would have something that says something along the lines of, interpret this drawing according to ASME Y14.5 M 1994. They reaffirmed that in 2009, 2004, they reaffirmed it. It takes them a long time to actually change the standard, and you can tell, I think the date down at the bottom right-hand corner says 1989 is when they actually came up with that chart. 1998, sorry, 98. It's been a long time ago. But around 2009, though, they updated the standard for the first time in many, many years. And they switched from being a green front of a book to now it's a white cover of the book. The FOPROL chart changed a tiny little bit, not its organization, but I actually brought it into SolidWorks and made a nice chart out of it and stuff. You can download this and look at it later. But it groups it groups the symbols into 5 categories. The form, orientation, profile, without location. It groups them up. It tells what kind of controls you can have, what kind of modifiers. Now, if you're going to use this standard on your drawings, now your drawings will say something like, interpret this drawing using ASME Y14.5, no M, dash 2009. Not very many people have adopted this. Most people are still using the 94 standard. You could still buy, until last year, you could still buy the 1984 standard from ASME. You have to use whatever standard is on the face of the drawing. Whatever drawing is called out, you have to use that standard. I have a collection of standards that go back to the 50s, just as ANSI and ASME was taking over, who was doing the writing and interpretation of the standard. If you switch to it on a lark and start putting this on your drawings, then from now on, those drawings have to be interpreted using this book, not the old green book. Most everybody in this room uses the old green book, right? You know what I'm talking about when I say the old green book? It's 1984. I see some heads and stuff. Is anybody using the 2009 standard right now? Ooh, more people than in Dallas area. Yeah, there's not too many of my clients or customers using it.
What's implied is there's no date?
That is not a complete call out. There is no date. You have to call out what year of which standard you're using. I sat through a GD&T talk this morning, and there's an actual ASME Y100, which is an all-encompassing one like the ISO one. That one does not need to have a year. Just call that one out, and it'll automatically call out a particular year of the 14.5. It'll call out a particular year. So it does need to have the year. You'll see, I see a lot of drawings with 73, 84, and 2009, but I haven't seen very many of them. But evidently we're going to start seeing more. The first lesson, after you get over the symbols, which you've already went back and looked at that archive of that, and you already kind of know how to put stuff onto drawings, the first lesson you get in geometric dimensioning and tolerances, the very first lesson the rule as it states in the standard is the geometric form of the feature can vary as long as it stays within the limits of size of the tolerance. That's a lot of big words for saying is that the size that you put on the drawings is the first control, the primary control for what your parts you're going to allow to come in. And that when you add GD&T to those particular parts and dimensions, you are refining what you're going to accept. But the first thing that controls the part is always the dimensions you put on the drawing. A very shorthand way of saying it is, the first magnitude is size. That's the first thing you check. It seems to bother people that GD&T is only something you slap on top of something after you already dimension it. Refinement, by refining a particular drawing or refining a feature, what you're basically trying to tell it is that you're going to check all the linear dimensions, all the angular dimensions first. You're going to check all of those size dimensions first before you ever check the GD&T. If your part's not 1 foot long and you ask for a 1 foot part long, does it matter if it's flat or not? You're going to reject it on the fact that it's not 1 foot and I ask for it to be 1 foot long. So GD&T is something you check later. The best example I can come up with that is thinking about surface finish. And when you look at surface finish, everybody here sees surface finish on a particular, on a piece of material. It'll either be done in micro inches or micrometers. It's a measurement of how rough the surface is. We control that with a symbol. Everybody's thrown that on a particular piece of metal or something. Someone's asked to do something. You can put these different numbers around the symbol, and as you put the numbers around it, you're telling them how wavy it can be, you're telling them how high it can be, how rough it can be, how rough between the different edges. You're telling them, if you put different other symbols on there, you're telling them if you can remove the material. Do I not want to remove the material? I don't care as long as it's got the particular surface finish I want. All of this stuff is I'm refining that surface. When you do that, I like doing this slide because the surface finishes, the very first surface finish uses the perpendicular symbol, which is exactly the same perpendicular symbol we use for in GD&T. The second one is the parallelism, and it's not the same symbol that we use in GD&T. In GD&T, we use two horizontal lines, 45 degrees, to imply parallelism. And there's a reason why we don't use the two lines this way. Does anybody know why we don't use two lines going this way for an icon? Equal. Yeah, it looks like an equal sign, and that's terrible. You want an icon not to imply other things. So I'm not complaining to the guys who did the surface finish guys, but they really should have used a better icon for parallelism. When you look at that, you don't start inspecting a plate for surface finish by checking the surface finish. The first thing you do when you're bringing a plate in is you check the length, width, thickness, everything that's on the drawing that defines what the part is. If any of those dimensions are out, you reject the part. You never waste the time of checking to see if it's smooth or not. That last inspection process of a part is you check the finish. That surface roughness is a refinement on the limits of size. And that's exactly what our definition of GD&T was you have the limits of size that control the part, and then we're going to do something to refine what we're going to accept, what geometry we're going to accept. Here it's surface finish. On GD&T, it's geometric shapes. If I go back and read that rule one more time, it says that I can have a feature and it can move and it can change its shape and it can do everything as long as it falls within the limits of size of the size tolerance. Okay? Limits of size. I've said that word like 10 times now so far, and I really haven't defined what limits of size is. Limits of size are the absolute minimum and absolute maximum value any particular dimension can have. We are used to seeing dimensions that say 0.25 plus or minus 0.05. Well, you actually have to do the math in your head and find out what the lowest number is acceptable and the highest number acceptable, and that's the limits of size. Those dimensions are allowed to be in that range, and it's acceptable. When you look at GD&T, then, if I'm going to refine that size, that means what I'm controlling has to be smaller than those tolerances. If my tolerance is 0.05, then my GD&T has to control something better than 0.05, because I'm already getting that control from just my limits of size. That's a big mouthful for limits of size. If I look at this particular part, here's one that's not dimensioned the way we probably would like to see it dimensioned, but it does what I want it to do. It has a lot of different features. We have a call out of a hole with a counterbore that has a particular depth. We have a radius. We have an angular. We have a reference dimension. What is the limits of size for a reference dimension? There is no limits of size because it is a reference. You would never use that as an inspector. You're not expecting the machinist to use that dimension either, but you're only giving that to us for information purposes. But all the rest of them the rest of them have tolerances to them of some sort. So if I look at this particular call out here for a square hole that goes through the part, it has a square hole, 0.065. It's plus 50 minus nothing. Well, then the absolute smallest that would be acceptable is 0.625. The largest that would be is 0.675. I'm not going to go through every one of these numbers, but you can kind of see we're trying to find out what the lowest one is and what the biggest one is. These are the limits of size for each one of these features. And let me get to one of these. Here's a good one. The 0.75 radius max. What is the minimum radius allowable in there? 0. Max. It goes all the way up to 0.75. It can't be any more than that. A common question you get from somebody was, if you're a machinist, would you machine that fillet on that corner up there? You would ship a triangle to the customer, right? And promptly get it right back, and they go, no, I wanted a fillet up there. Right? That's kind of how this goes. But truthfully, from the standard, what's acceptable is 0, and 0 is a sharp edge. So a triangle would be completely acceptable to ship and make it fit in here. And that's a problem we have is between, how many people here did the GD&T training class this morning? One of the questions that popped up this morning was about gauging versus this. And one of the gentlemen asked a question was, how do we bring everybody together? And my answer comes from an old Star Trek episode. Captain Kirk told the alternate universe Spock how he could change the world by just keep forcing it and forcing it and forcing it. Forcing his will on everybody, and I'd say the same thing about GD&T. Just keep putting it on drawings and keep rejecting it from machine shops and training the machine shops, training your own inspectors, and eventually we'll all get on one page. I don't know another way of doing it. I've had designers who've put that on drawings and they go, no, I really meant it to be 0.25 to 0.75 is what I wanted. I said, well, then that's not the tolerance you put on there. The tolerance you put on there was 0 to that. If you wanted 0.25, you should have put 0.75 plus nothing minus a half. So it's kind of funny, you start talking through things, you realize that people got exactly what they wanted or didn't get exactly what they wanted. But if they talk it out loud, they get exactly what they need. The rest of these kind of all make sense. And of course, the 0.25, the 2.50 across the bottom has no tolerance. It's just a reference. So any feature that comes in and it falls within those ranges of those numbers, that's the limits of size for this particular part, for each particular feature inside this part. I have to take a little aside right here and ask a question of the group. Is there a difference in the connotation of what it means to people if you see this on a drawing between 0.150-150, which everybody here agrees that means that that feature is 0.100 to 150 is acceptable, right? Is there any difference between that and 0.125 plus or minus 25? Is there any difference? I got yeses and nos, which is good. Answer number one is they're identical. They give the same limits of size. As far from a GD&T standpoint, they're identical. They have the same range. But somebody said the word connoting. What's the connotation of it? Answer number two is, if I was a manufacturing guy doing this, what would I target? I would target 125 if I'm the right-hand side and let it go both ways because I want my maximum yield. Right? If it's a standard kind of a process. But what if it's drilling a hole and all that's going to happen with me is my drill pit's going to wear out and my hole's going to get smaller and smaller and smaller? What would I target then? I would target the biggest hole. I would start drilling my hole at 150 knowing that as my tool bit wear out, I'm going to get closer and closer to 100. So the first parts you get are going to be at 150 and over the life of the program they're going to get all the way down to 100. And then he's going to buy a new drill bit, because you're really cheap and you buy really cheap equipment. So it's two different ranges of what are you trying to target for. Answer number three is, what would you put on the CAD model? If you see 150 to 100, did you model at 100 and know that it was getting bigger? Did you model at 150 and know it was going to get smaller? Did you model at 125? So there is a connotation different between who the modeler is, what you're trying to tell the person is. And my answer to this from a GD&T standpoint is, I want to see the one on the right-hand side. I want to see what your target is. My target was I was trying to get an 1/8 of an inch hole. So I gave him my target, 125. And oh, by the way, I don't care if you miss it bigger or smaller. but my target's 125. The one on the left, 100 to 150, I've given him no design intent whatsoever. All I've told him what's acceptable. And although it's not a rule of GD&T, that's what we're trying to do with geometric dimensioning tolerancing, is we're trying to impart as much design information as we possibly can into the model and into the parts, into the drawing. So I would always put what's on the right, not what's on the left. Are they both acceptable? Yes. Another little baby aside here. In the 1994 standard, there is one call out in there. And at the time, it was a controversial paragraph to be added. And the paragraph reads, if CAD/CAM database models are used and they do not include tolerances, then tolerances must be expressed outside the database to reflect design requirements. That means if you had 3D CAD models, you had to give somebody a drawing. What it was trying to say, it said it with a negative, was, oh, by the way, if you can put those tolerances inside your 3D CAD model, you don't have to make a drawing. And that's why it was controversial in 94, was, you mean we can make parts without drawings? As long as everything's embedded inside the model, we can? And like I said, it says it with a negative, and it's one paragraph, and it's the only paragraph in a book that's about this thick, is it mentions the fact that we might be doing stuff in the 3D world. Flash forward to 2009. 2009 states, under its documents of what you can use, it cites the -41-2003 standard that says, here's how you do 3D product definition in the 3D world. And it gives all the rules for what do you do to embed dimensions and tolerances inside of a 3D model, which means I can have a drawing or I don't need a drawing. All my data is inside my 3D model. It provides guidance for what you're supposed to do, and people like SolidWorks and all the other guys are following that when they do produce their files, if you use any of the standard formats, Parasolid, Step 203, Step 214, they don't do it in IGES, but if you do it in any of the standard 3D models, they include the data per this standard. There are numerous citations. This standard is about the same thickness, and now throughout the entire book they realized by the year 2009 that we're all using 3D computers, so they better mention the fact of here's how you do it if it's going to embed it inside your 3D data. It got mentioned by one of them. I was given this class before, and they said, oh no, it's real well documented in 1984 because of this. And I was like, in 1984 there was only a handful of 3D CAD systems. And that's when they wrote the standard. They kept reaffirming it, and like I said, that one paragraph was kind of even a controversial paragraph when they added it. Let's get back to what we were talking about, was limits of size and stuff. If you saw a part like this, a drawing like this, you'd see that its overall length is 5 plus or minus half. Its overall height is 3.5 plus or minus a half. If you look at that particular model, I've drawn some little hidden lines inside and outside. That inside is the smallest the part could be. The outer one is the biggest the part can be. They have very special names in the GD&T world for that. We call the one on the inside, we call that the least material condition. It's how does the part weigh the least? So it's the smallest that plate can be. I drew the lines on the outside is how do we make that part weigh the most? Well, if it's on the very biggest size, then it's the maximum material condition. I like thinking of it as a weight because if I drill a hole in there, what makes a drilled hole maximum material? Well, how do I make it weigh the most? I drill the smallest hole, so I'm trying to make it weigh the most. So maximum material for a hole, for negative features, it makes them small. For positive features, it makes them big. And that kind of makes sense if you're trying to fit two things together. That kind of makes sense. I'm trying to get everything. I want the plates to be the thickest. I want the holes to be the smallest if I'm trying to put this stuff together. LMC, almost no one ever uses the least material condition. There's a very famous example in history that there's one particular company out there. Did anybody in here drive a Javelin? It's very, I see two hands raised up. It's very famous that they did not do a least material condition. We call that a clearance analysis. And the gaskets they put around the doors were less than the clearance between the manufacturing process. So as they were producing cars that you could see from the outside to the inside. even with the gaskets closed, everything like that, and they leaked very badly, and they sounded terrible going down the road, a lot of road noise. So we don't do a lot of least material condition analysis, but we should. We do a lot of maximum material condition analysis. We're trying to make sure things fit together. It used to have a different name. In World War II, when the GD&T standard was just starting, 45 to 49 when it was starting, it had a different name. They didn't call it maximum material condition. They called it the worst case scenario. And sometime around the 60s, they decided that sounded too militaristic and too bad, worst case scenario, and they changed it from that to maximum material. So, but we do maximum material because we're just trying to make sure things fit together all the time. But that's the two limits of size, the smallest that something can be and the biggest something can be. Well, if I look at those two same things, the gray thing is, this line here is my least material, and there's my maximum material, and the yellow was my target. You see the off blue purplish color part? That's the part I got from my machine shop. I have a really bad machine shop, and that's the part he sent me. Do I accept that part? I have to accept it. He is completely within inside the limits of size all the way around. I have to accept that part. I do it cringing and realizing that I'm never going to send you another part again, but I have to accept it because it matches my stuff. But let's ask a question from GD&T. What if I needed one of those edges to be straight? What if it was kind of important that one of them be straight? Well, the first answer I could do, how would I make it straight? I hadn't had a GD&T class in a while. What's the first thing we would do? Tighten up the linear tolerances. Instead of it being a ½ an inch, plus or minus ½ an inch, I'm going to start making it plus or minus 2 mils, plus or minus 3 mils. If I start doing that, I'm definitely going to get straighter parts, right? The parts will be acceptable will now be, I've got a much smaller range of what's acceptable. The problem with making a tolerance change from a ½ an inch, plus or minus ½ an inch, to plus or minus 2 mils, the difference in that, though, is all of a sudden now my part cost went up a lot. My yield went down a lot, and probably my time to manufacture, because he's going to make 16 or 17 plates before he gets one that's good, right? So my time is going to slow down too. So all I really wanted to do was a straight edge. All I wanted to do was refine one of my edges. Well, as soon as I start saying like that, how about if I just try to control the shape? We need some kind of shape control, something we can put on a drawing that changes what kind of shapes we're going to allow. Instead of calling it shape control, how about we call it geometric dimensioning and tolerance. Geometric, we're going to refine what geometry we're going to allow for an acceptable part. Anybody remember the towel? The idea was if you were hitchhiking through the galaxy and you had a towel with you, you must have all your stuff together. Because you had enough to have everything together and you had your bath towel. If you didn't have your bath towel, you must not have anything together, and you're not worth being picked up. Well, we don't need a towel in lieu of having a towel, but we do need some GD&T learning on what kind of controls can we put on things and how do we control them. And that's going to be our towel today, is that knowledge. It's a stretch, I'm sorry. I needed a joke there. I already talked about the symbols, like I said, a couple of years ago. You all can review that. We've already talked about modifiers a couple more years ago. You can kind of review that. What I'm trying to do today is what I want to talk about was the tolerance zones and shapes. What does the GD&T control? What's acceptable, what's not acceptable when you see it on a drawing? It sounds like the same thing. It sounds like tolerance zones, tolerance shapes sounds like the same thing, and they are linked together, but they are two different things completely. We can have a cylindrical tolerance zone. When we have a cylindrical tolerance zone, it's just like it sounds. That's what I'm allowed to do, is a little circle of what's acceptable and what's not acceptable, is a little circle, cylindrical tolerance zone. What shape is total wide? If I have cylindrical on one side, my other side is total wide. Total wide has a lot of different shapes. And that's where it starts getting complicated, is what's acceptable, what kind of controls are you getting by using these other geometric controls that aren't controlled with a cylindrical tolerance zone. We have just a pinch. Not that kind of pinch, but that kind of pinch. The size of a total wide, whenever I'm teaching these kind of classes, and usually it's a lot smaller class than this, whenever I teach this class, I'm always doing this with my hand. I put my finger in for it, and I'm doing like that. That's how wide total wide is. It's the distance between my finger, my thumb, and my forefinger. That's how far total wide is. Now, it depends on how you move your hand. That's the trick with GD&T. That's how wide total wide is. It's that wide. But if I'm doing straightness, it's this. If it's cylindrical, it's this way. If it's profile, it's this. It's how I move my hand. It's not the distance between my finger and my thumb. All controls, all 14 of the GD&T controls have a total wide tolerance zone, except for one. Concentricity, whether two things have the same center sounds like cylindrical tolerance zone. That's the only one that doesn't have a total wide. The other 13 all have total wide tolerance zones. 5 of them, okay, so we had 14, we down to 13. 5 of them can be further modified. They don't have to have total wide. They can have cylindrical tolerance zones. The most famous one is position. Position, you're positioning holes, you're positioning bosses. They almost always have a cylindrical tolerance zone. We add that modifier to make it a cylindrical tolerance zone. But in addition to concentricity and position, the other 3 are parallelism, angularity, and perpendicularity. That's the orientation controls. We can orient bosses. We can orient holes. So those have cylindrical tolerance or could be modified with cylindrical, position, and concentricity. There is a really weird exception. I'll talk about it at the end of this thing. I hate talking about GD&T and you say, well, here's the rule and here's except there. Here's this and except here. So I try to keep all the exceptions at the end. The one exception I'll come back to is I'm going to talk about straightness of shafts, and we're going to talk about why you can put a cylindrical tolerance on a straightness. It's got a very weird reason why it can do in very unique positions. It can have a cylindrical tolerance zone. So there's the 5 that can have cylindrical tolerance zones. Concentricity must use a cylindrical tolerance zone. There's a lot of discussion in the groups about whether you actually have to put the symbol or not. I'll talk about that in a second. But if you look at 2 different ones right now, if I have no symbol, I've got my feature control frame for GD&T, the one across the top, I've got parallelism. I have no symbol before the .014. There's no symbol occurring there. If I have no symbol, then it's total wide tolerance zone. That means I use my little finger like this, and that's how big my tolerance zone is. And because it's parallelism, it means it's parallelism. It's going between 2 parallel surfaces. I know how to move my hand back and forth. So that's total wide. If I put the modifier of the diameter symbol before that number, all of a sudden that changed all of a sudden now. That means that 0.002 tolerance at the bottom is not total wide. It is now a cylindrical tolerance zone. It means I'm positioning something where the center of that something falls within a circle of 0.02 around. I know the diameter of that little circle that's acceptable. Okay? So I'm looking for that symbol or not looking for that symbol. I know what I said a second ago was if you see concentricity here, because the total wide is a cylindrical tolerance zone, there's some question about whether you really got to put the diameter symbol here or not. I always do. I want to see that diameter symbol there. I want to see that concentricity. I want to see that cylindrical tolerance zone there. It might be redundant. I cannot find it in the standards. I've been to 1 or 2 of the GD&T conferences where they talk about it, and there's no good consensus. I imagine the next release will have that really defined why you should put it there or not put it there. Each of the 14 symbols, except one, concentricity has a symbol, they all have a total wide. And that total wide tolerance is kind of, makes sense. It's part of the name is how we get to it. If I'm looking, sorry about this. If I'm looking here, if I'm trying to control form, remember FOPROL, form, orientation, profile, run out, location. The first control there is form. If I'm looking at form control, what is, if I'm saying 2 things are straight, I use the straightness call out. I'm basically looking at 2 edges. Okay, if I'm looking at 2 edges, it means I've got my little fingers right here and they're tracing that edge. What's acceptable? Above it and below it. Very important. If I don't tell you anything different, then it's the same amount outside and inside. It is uniformly distributed. Again, during the exceptions course, I'm going to talk about how you don't use it uniformly above and below. But right now, it is a little finger, and it traces my line, and that's what's acceptable and not acceptable, right along the line. That's straightness. For flatness, I can still use my little hands like this and say it's all over the whole surface, but maybe you want to prefer to do this and go, flatness is between two planes. And as long as every point in that plane is between those two planes, what's the maximum and the minimum, as long as it's in there, that's an acceptable flatness. For circularity, I've got two circles. I've got the inside and outside. Again, I use my little fingers, I just trace a circle around it. One of them is inside my feature, one's outside my feature. I just trace it right along here. My last one is cylindricity. It's two different things going down through space like that. I usually think of those like little force fields, and if the part comes inside or outside those, it's not acceptable. But as long as it's within that little sleeve of goodness, I'm going to accept the part. But does everybody see that that's total wide? The distance between those, the inside and the outside, is that total wide. And where's the center of that total wide? It's my part that's on the drawing. That's my minimum. That's my part on the. That's good. And as long as it's between my fingers, everything's okay. Now that's a really bad inspection tool. Is you hold your two fingers together like this, right? That's kind of bad. Somebody giggle. Come on, please. Okay. A better thing would be like a coordinate measuring machine or a vision machine. And if you're older, like people like me, you remember the times when we used to put things on optical comparators and we'd produce a 10x or a 20x overlay. And the overlay was we would draw the maximum and the minimum, and we'd do it in a particular thing. We'd lay it on the chart. We'd lay the part on there, and if the part fell within the overlay, then it was acceptable part. We didn't measure every dimension. We just looked to see if it was inside or outside those overlays. So you can see why GD&T, that's something that people kind of forget. GD&T speeds up inspection a lot. If you inspect it correctly, your inspectors go much, much faster. They're one of the ones that seem to always complain and slow down the system. When you put GD&T on a thing, you've made it much easier for them to check things than in the old days. So it's one of those fights that's a weird fight. You're fighting them to make their life easier, and they seem to be fighting back, and I've never quite figured it out. Machinists is a different story, but the inspectors, it helps their life out quite a bit. That's form. We go over to orientation, or before I do form, here's some different drawings that have form controls. And if you take my class or you see my stuff on that, we talk about two-dimensional, three-dimensional, two-dimensional, 2D, 3D, 2D, 3D. The form controls are straightness, flatness, two-dimensional, three-dimensional, flat, and then we have round, circularity, cylindricity, 2D, 3D, 2D, 3D. The 2D, if I'm just looking at this particular shaft up here, two-dimensional, I got a half-inch shaft, and I'm saying that it has to be straight within 0.003. That axis that is formed down through the center of that part, I'm saying it has to be 0.03. If I go to the right-hand side, I'm looking for flatness. I've got a part that's 1.650 plus or minus 5 mils. I have a flatness of 0.02. Someone in this room is thinking, well, why? That's a kind of a small tolerance anyway. Why didn't he just change this tolerance to 1.65 plus or minus 0.02? Does everybody agree you get the same result? I'm now controlling something within plus or minus 2. It's true, but does everybody agree that it's a more expensive part to say that it's plus or minus 2 versus plus or minus 5? I'm letting them have a bigger range of what's going to be acceptable for thickness, but I'm telling them that that top needs to be flat. I like it from a design standpoint because I've just told them that that top of that part is important to me. I did it by putting the flatness on there. So I told him how thick the part needed, and I told him what was important to me. Bottom left-hand corner, I have a two-dimensional round. I have that same shaft I had up above there, but on this time on the shaft, I said it has to be circular within that. It means I'm not letting it grow as it goes down the length. I'm not letting it get out of circularity. For cylindricity, the bottom right-hand corner, I'm looking for cylindricity. That's the same as circularity, but instead of checking it on any particular cross-section, it's over the entire length. I usually tell a little joke here somewhere along the way. Does everybody see the symbol for cylindricity is a round circle with two lines like this? And the reason why it's that particular symbol, that's a parallel circle. Has anybody in here ever used a drafting template? There's a couple of us that are old to remember drafting templates. Drafting templates did not have the letter Q. They had an O, and if you wanted to do a Q, you had to slide the O over, and that's how you drew a Q. Anything that was repeated, they didn't put on there. So, for concentricity, there was never a symbol on the GD&T little thing that Avery used to produce. They never had a cylindricity call-out. What they had was, you used the circle call-out, and you used the parallel, and you shifted the parallel back and forth to draw the two lines. And if you think about it, what is a cylinder? But a cylinder is a circle that's parallel through space. Circle, so it even kind of made sense why they picked the two symbols and why they grouped them together. But it's because of a throwback to when we used to use little green templates to make drawings. I'd love it if they updated the icon, actually. I've asked a couple times to change it to like a little Coors symbol. I'm not a Coors fan, but a Coors can would look more like a cylinder to me than that particular symbol. So that's the different controls for form. When we look at orientation, we had the orientation. We said orientation could be changed to be a cylindrical tolerance zone, but it can have just a total wide tolerance shape one for these particular ones. So if I'm looking at here, I always thought this is kind of funny. When I control if two plates are parallel with each other, I get a freebie when I check to see that. I get a free analysis there. I get a free thing. I'm controlling the flatness. If I say that two planes have to be angular within each other or perpendicular to each other, one of the other things I'm getting for free is those two surfaces have to be flat. I always thought that was kind of cool. It's a free control because it's the same control as flatness for that surface. It just happens to be like that. So it's a free control. The thing is we'll even show there's some ways I could get around that control by using tangent planes. I can get away from that saying, I don't want it to be flat, but I need it to be perpendicular, which sounds funny, but you can actually do that. That's the shape we're getting. If I look at the top left-hand corner, I've got a datum. That's the first time we had to use the word datums. But orientation, to orient something, I have to orientate something to respect to something else, so I have a datum call out on the bottom. So here's my datum. My top surface has to be parallel with my bottom surface within 0.5. So I've got my little fingers apart, and they're 0.5 millimeters apart from each other. They're going back and forth this way. But look at the overall tolerance on the whole part. It says, I don't care if it's 100 plus or minus 1. It can be thicker or thinner from 99 to 101. I don't care how thick it is. But once you start machining it, I want it not to change more than 0.5 millimeters. I have refined what I'm going to accept. Instead of changing that to 100 plus or minus 0.25, which would give me the same thing, but it would be 4 times stricter of a size tolerance. Bottom left-hand corner, I have to add 2 things. I add a datum across the bottom, but I also have to have a basic dimension because I'm going to check angularity. And I'm saying that slope surface has to be angular within 0.4 of datum A, which that 0.4 is I put my fingers at 0.4 millimeters for each other and I trace it back and forth this way. Everybody agrees that's completely different than if I just had 40 degrees from that surface with no basic, no line around it. If I had that, does everybody agree that that's a pi wedge? The tolerance would be a pi wedge shaped. At the bottom left-hand corner, I'd have a relatively tight tolerance, and the further I got away, the pi wedge keeps getting bigger and bigger and bigger. What's acceptable? That 40 degrees would move back and forth. Because that 40 has a basic dimension, it means it's 40 perfectly. It's theoretically perfect at 40 degrees. I got the 0.4, which means it goes 0.4, so it's a uniform surface. My little fingers are apart. 0.4, 0.2 above, 0.2 below, all the way across there. That's what's acceptable. If I look on the right-hand side, I got a perpendicular. I got my bottom surface set up as my datum A, and I said that left-hand edge there has to be perpendicular with respect to datum A within 0.5. So 0.25 inside, 0.25 outside. I got my fingers that far apart. That's what's acceptable to call that part. Form, orientation. Next will be profile. We have 2 profiles. We have 2-dimensional profile and 3-dimensional profile. We have a surface profile of a line, profile of a surface. I'm not in love with the icon with this either. The icon here is a half circle. I don't love it, but you can kind of imagine more like a corrugation. That would be a better icon for profile. I'm trying to trace the profile. You've given me the theoretically perfect, and I've traced it around. That's what's acceptable as long as it's inside that profile. profile of a surface is now I'm doing it like this and now I'm moving in 3D, that's acceptable. Kind of a force field out there in space. As long as it's above or below, it's acceptable. And if it breaks that force field anywhere along the way, it's not an acceptable part. Runout's one of those weird ones. It only has total wide, but it's a little needle moving back and forth. There's only one piece of equipment on the face of the planet up until a few years ago that could measure runout, and it was a dial indicator. Until the last 10, 15 years, that's the only way you could do it. You had to put a dial indicator on it, watch the little dial indicator, watch the little needle move back and forth. You could tell if something had run out. Nowadays, with some of the laser inspectors and coordinate measurement machines, they can actually map that from a 2D to a 3D, and you don't actually have to do it. They turn the laser turns the 360 degrees. Runout always requires that you rotate the part around one rotation. It's the only way you can measure runout. But you're watching that needle move back and forth. But like I said, within the last 10, 15 years or so, they can actually do that now without moving the part. They're moving the measurement tool. It's kind of cool. So, But when you look at that and you look at the needle move back and forth, that's the total wide is how much is that needle moving. Profile call out, I like this because there's only there's two dimensions on here that are size dimensions. The overall length, 30.30 is the overall length, and the length at the two ends is 95. But this is a weird prescription of some kind of a two-dimensional lens. And you can see that each point is theoretically controlled how high it goes. It has a particular prescription. And here's my basic dimension here. So each one of these points, and it goes smoothly through that point. So again, I would use my little fingers apart, and I'd have 0.25 below and 0.25 across that surface. This also adds something around here too, do you see I have a D pointing here and an E pointing here? Those don't have a square around them. They're not datums, they're identifying points. And I put that on a particular drawing because I'm saying, I'm checking the profile of this surface from here to here, only between D and E. I'm not checking the tolerance here, 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 or here. So I can limit, very easily by identifying particular points, I could limit why I'm going to check my part. And again, I'm trying to refine what's going to find acceptable. I have seen parts just like this one where they have identified D and E inside here. Because manufacturing, they couldn't get manufacturing at the very edges, but they can get it very smooth on the inside. So they actually move this D and E point to the inside here and say, I'm only going to inspect it from here to here to make sure it's actually profiles okay. I don't care what's happening on the ends as much. Does everybody kind of follow that? So that's profile of a line. Runout control, like I said before, we're trying to look at that needle move back and forth. I'm going to grab the outside edge of this on the right-hand side. I put my needle on the right-hand end of the little bore, and I rotate it 360 degrees. Because this is total runout, there are two of these little arrows. That means I would move my dial indicator back and forth along the surface, and I would never re-zero it. Because I'm looking to see if there's runout going this way, and I'm running out as they're going down that length. If this only had one arrow down here, it was circular runout, I would do everything I just said. I would drop my dial indicator here, I'd rotate it around, I'd move my dial indicator here, I'd rotate it around, and I'd move down that length. But every time I moved it down the length, I'd hit the zero button. I'd re-zero it. Because I'm not checking down the length. I'm not checking the total runout, I'm only checking the circular runout. So that's the difference between one arrow and two arrows. No, it grabs the outside of it. Because it's in line, I apologize, it is the datum. Because this datum is in line with this, it means it's the datum axis down the center. Well, it gives you one theoretical axis. One theoretical axis. He asked a great question. Because this datum A is in line with this dimension, it's actually the center of that dimension. If they move that over a little to the left or a little to the right, it means that outer diameter. It means you chuck up on the outer diameter, and that's what you turn in your mandrel. So by being in line, it means I'm driving it to the axis, down to the center, versus I'm just grabbing that particular edge. Position, The position geometric control is the very first geometric control. It's the one that started in World War II. I always think it's funny because it looks like a little target bomb, like you're trying to bomb something. It's the first time that people were drilling plates in one state and taking those plates to another state and assembling a tank or a plane. It's the first time we were drilling that many holes trying to put stuff together. So that was the first geometric symbol, was the target symbol, the position symbol. The other two location ones are symmetry and concentricity. Symmetry is one that people just absolutely fall in love with. They go to a GD&T class and they want to throw symmetry on a particular drawing. And unless you design teeter-totters or rotor aircraft, you should never put the word symmetry on your drawing. And I do not mean you should put the little center line symbol. The center line symbol is not in the standard, but that's a good, lazy way of making drawings. Everybody agree with that? You put the little center line, I only dimension one side, I put the little center line on there. What is that telling you on a drawing when you see a drawing with a little center line there? It means I'm lazy. It means I only threw a few dimensions on here, but I want you to use those same dimensions everywhere else. If I put those dimensions on there and put this here and say I want it to be symmetric control, what it's telling me is if you miss this hole to the left on this down here, where does this hole here have to miss? To the right. It has to be exactly symmetric. We're not measuring it within where its target area is. We're measuring it to where its master is, where the other part is. And it even gets more complicated when the patterns are not nice patterns. So symmetry is one of those things that it's not the same as a center line. And people come to class and they just absolutely love it. The other one that gets people in trouble is concentricity. Concentricity is I'm trying to make two things concentric to each other, and it's wonderful that SolidWorks has that as a mate. I absolutely love it. I use it all the time, but it ruins you for GD&T because it's one of those ones that you never put on a drawing. If I put concentricity on a particular drawing and I'm trying to say that two things are concentric to each other, that means they have to go put on an inspection machine, a vision system or CM, find the imaginary axis of one part, find the imaginary feature of the other feature, and measure the difference between those two imaginary axes. Can you do any of that with a pair of calipers? Can you do any of that on a surface plate? You can't do any of that. What you probably really meant for is you wanted one thing to be positioned within the other one. You probably wanted one of the other controls. Lots of times you either want run out. You want one thing to be run out to the other, which is easy to do. That's easy to inspect. Even though the part may be a square part, I can still check run out. I put one part on here and I just spin it around and look at the other surface. Run out is an easier thing to measure than concentricity. Again, people come to class, they're used to saying that word concentricity, and they throw it on drawings. But it's extremely hard to measure. Position, a little easier to measure. I could have easily thrown a drawing up here that just had drilled holes in it, and here's the position thing, and everybody's seen that. They have the little cylindrical tolerance on it, and we're trying to find out where that hole is. What I did here was slots, because I can position anything. I do not have to position holes. When I position this hole up here, you'll notice it doesn't have the little cylindrical tolerance zone here. What it's saying is that the center of this slot can move up and down 6 mils. 6 thousandths above and 6 thousandths below. That total wide of 6 above and 6 below is 12 total. 12 total. And I've told me we're theoretically perfect where they occur, and I've told you where they can be positioned at. That's an unusual control. People think when they say the word position, they think they're drilling holes. They think that's the first thing they're doing. Holes, bosses, screws, mounting things. But it can position anything. Now we get to the exceptions. Rule 1, remember what rule 1 was. Size is the first order of magnitude of control. Size is the first thing we're going to inspect for. GD&T is only a refinement. Everything says that if you don't measure it to the dimensions on the drawing, I reject the part. Well, there's 4 exceptions on why you don't just measure the part. Number 1 was if you buy stock items. If you buy a 2x4, you don't actually put a measurement on there and measure it 2 inches by 4 inches. Everybody realizes you get cheated anyway, right? 2x4s. You buy gauge 12 wire. You don't put a pair of calipers on that. It's one of the things that you don't measure it against a catalog. It's a thing between the lawyers or the purchasing office. Did you really get what you bought? But you can't actually put a pair of calipers on there. There's nothing on a drawing you can put on there to measure 12 gauge wire. Anything that's formed with stock, anything that has those kind of stock items. Parts that are subject to free state variation. If you buy an O-ring or you buy a piece of flexible rubber, You can't put a pair of calipers on there because as you did it, you'd been imparting a force on it. Imparting a force on it means it's not free state. It means you can't measure it. So you don't check to see if something's flat because it's a piece of rubber, just because it's all coiled up on your part. If you actually put on a note, this note that says perfect form of MMC not required, you can also stop it and not uncheck it. Or if you put straightness tolerance on a feature of size with maximum material condition, that's a lot of ifs and buts. But if I try to see if a shaft is straight at maximum material, the shaft is straight means the shaft is as big as it can be and it's straight. It can have a curve to it. That's the important one, and we see this one all the time. We see this particular thing. I'm trying to tell you that shaft is 0.500 plus or minus 2 mils. And its control is I want it to be straight within 0.015 at maximum material condition. Wait, 0.015 is much bigger than the plus 0.02. That's not a refinement of GD&T. I expected this number to be much smaller than this number, and it's much bigger. It's because I'm allowed it to not be straight. It means I'm going to make this shaft, it's going to be 22 feet long. And when I ship it to you, it's going to smile like a smiley face. Right? Or if I grab it on the ends, it's going to be a smiley face. If I grab it in the middle, it's a droopy frown, right? But what I'm allowing it to do is how much am I allowing it to change from one end to the other end? I'm allowing it to change by 15 thousandths of an inch from one end to the other end. Does everybody make sense? It's a really rare example, but you do see this every so often. You'll see this for straightness. There's 2 new symbols we have to worry about. I keep telling you over and over again that we have the same inside and outside of the tolerance stack up. The new symbol in 2009 is called an unequally distributed tolerance. If I do that, I have 0.5 U with a circle around it, 0.5. It means I have all my tolerances to the inside of my part. 0.5 U0 means I have nothing to the inside. I only allow you to add material. Sound familiar? Like we're back to the old surface profile type stuff where they're trying to things. And the last one was 0.5 U with some other number. If I have the 0.1, it means I'm allowed to have 0.1 outside and all the rest of it 0.4 on the inside. So it's completely unequally distributed. A better example, and what I call it is how much is out. After I see the U symbol, I'm going to tell you how much I'm allowing you to have outside the part. If I look at this, here's one, just a profile of 0.8, and I'm not telling you anything. So everybody knows that's 0.4 outside, 0.4 inside, equally distributed. Over here I have 0.8 U0. How much is out? 0. So what am I allowing? It's all 0.8, but it's all to the inside. Here's 0.8 U0.8. That's still 0.8 wide, but it's all to the outside. I'm not allowing you to come inside my model at all. And finally, here's one that's just a weird one, 0.8 U2. It means I'm allowed 0.2 outside, 0.6 on the inside. Still 0.8 wide, but it's where is it positioned?
Do you need that basic dimension of 0.2 there, or is that just to explain that?
That's the old method. The old method, you put a chain line in that. I'm sorry, you do not need this chain line anymore. I don't need this chain line. I don't need the chain line or the thing. This is what you used to do in the old days. This is what you could do now. This is what you did in the old days. This is what you do now.
If it doesn't say the U is 8 for both sides or just the middle?
It's the first one is the total amount. U is how much do I let on the outside. So you never have the U with nothing. Either leave it completely off,
Yeah,
or
that means it's 0.8 above and below, or
0.8 is total wide. 0.8 is total wide. The other one is how much is going to be outside. So the first one is how wide it is, total wide. Catch me right after this real quick. They gave me the 2-minute warning here. I'm trying to the hook. If you see this on a particular drawing, I'm seeing this, I'm allowed this to be 0.1. I get a free GD&T control of flatness of 0.1 from one end to the other end of this part. This part's relatively long. Do I really care that it's flat? Or when I put it in my assembly, is it going to flatten it itself? There's a new symbol. It's called independency. I put an I with a circle around it. What it's trying to tell me is I don't need perfect form. I'm an old school guy. I would have used the Ghostbusters no symbol and put PF, no perfect form. What they did was they're trying to tell me that it's independent of each other. By putting the independency on here, the same drawing I just saw a second ago, I'm saying this dimension controls it within 0.1, but independent of that, I'm going to give a flatness of 0.5. And does everybody realize that that 0.5 is a much bigger number than the 0.1 of my limits of size? But what they're saying is, anywhere I put my calipers along that entire length, it had better measure 10.7 to 10.8, anywhere I want to put my calipers. But over the entire length, I'm going to let it either a smiley face, a waffle, I'm going to let it do something, but as long as the waffling doesn't happen more than 0.5. Does that kind of make sense? That's how I'm trying to key those two together, because I'm getting a free flatness here that I didn't want. I don't want them to inspect it for flatness, so I'm trying to make them independent. Finally, the big wrap-up. So long, and thanks for all the fish. Again, if you read the book, we are the third smartest creatures on the face of the planet. The mice, the dolphins, and then us. So we're the third smartest ones. And you're now the highest of the third one, because now you got some GD&T under your belt and stuff. So I'll stick around for some questions afterwards. Thank you all very much. I hope you all had the same thing I did for SolidWorks.